HVM, a parallel evaluator for interaction combinators. Victor Taelin, abstract. We present HVM, an efficient, massively parallel evaluator for extended interaction combinators. When compiling non-sequential programs from a high-level programming language to C and CUDA, we achieved a near-ideal parallel speedup as a function of cores available, scaling from 400 million interactions per second to 5,200 MIPS to 74,000 MIPS. In this paper, we describe HVM's architecture, present snippets of the reference implementation in Rust, share early benchmarks and experimental results, and discuss current limitations and future plans. This paper is a work in progress. It will be continuously updated on HVM's repository as it is written. 1. Introduction. Interaction combinators were introduced by Lafon as a minimal and concurrent model of computation. Lafon proved that ICs were not only Turing complete, but that they also preserved the complexity, class, and degree of parallelism. Moreover, Lafon argued that while Turing machines are a universal model of sequential computation, ICs are a universal model of distributed computation. The locality and strong confluence of Lafon's ICs make it suitable for massive parallel computation. This heavily implied that ICs are an optimal model of computation in a very fundamental sense. Yet, it remained to be seen if the system could be implemented efficiently in practice. In this paper, we answer this question positively. By storing interaction combinator nodes in a memory-efficient format, we're able to implement its core operations as lightweight C procedures and CUDA kernels. Furthermore, by representing wires as atomic variables, we're able to perform interactions atomically, in a lock-free fashion and with minimal synchronization overhead. We also extend our system with global definitions and native numbers. The result, HVM, is an efficient, massively parallel evaluator for ICs that achieves near-ideal speed up to at least 16,384 concurrent cores, peaking at 74 billion interactions per second on an NVIDIA RTX 4090. This level of performance makes it compelling to propose HVM as a general framework for parallel computing. By translating constructs such as functions, algebraic data types, pattern matching, and recursion to HVM, we see it as a potential compilation target for modern programming languages such as Python and Haskell. As a demonstration of this possibility, we also introduce Ben, a high-level programming language that compiles to HVM. We explain how some of these translations work, and set up a general framework to translate arbitrary languages, procedural or functional, to HVM. 3. Syntax. HVM syntax consists of an interaction calculus system which textually represents an interaction combinator system. This textual system is capable of representing any arbitrary interaction net and therefore possible to represent vicious circles. We only consider HVM programs which do not contain any vicious circles. HVM syntax has 7 different types of agents or nodes. Additionally, HVM also has variables to represent wires which connect ports across nodes. Trees are either variables or nodes. They are represented syntactically as. Notice that nodes form a tree-like structure, and throughout this document we will make systematic confusion between nodes and trees. In the interaction rules, it is critical to know when a variable is permissible or not when referring to arbitrary nodes. In memory layout, however, we purposefully blur the line between nodes and variables as the memory layout is greatly simplified by doing so. The first 3 node types are nullary, and the last 4 types are binary. As implied above, VAR can be seen as an additional node type. As in Lafon's interaction nets, every node has an extra distinguished edge, called the main or principal port. Thus, nullary nodes have 1 port, while binary nodes have 3 ports. With the syntax above, the main port of the root node is free, as it is not wired to another port. We can connect 2 main ports and form a reducible expression using the following syntax. Regex equals tree tilde tree. The net consists of a root tree and a list of unseparated regexes. HVM nets represent what are known as configurations in the literature. A net like T and V tilde WN and VN tilde WN graphically represents a net like figure 1, a configuration, modified image, where omega is a wiring. Thus, HVM nets contain only a single free main port. Wirings are possible between trees through pairs of VAR nodes with the same names. Note, however, that a variable can only occur twice. This aligns with interaction nets in that a wire can only connect two ports. Lastly, the book consists of a list of top-level definitions, or name nets. Each HVM file contains a book, which is executed by HVM. The entry point for HVM programs is that main definition, 3.1. An example, the following definition, such equals, represents the HVM encoding of the lambda calculus term lambdas, and can be drawn as the following interaction combinator net. Notice how con/DUP nodes in HVM correspond directly to constructor and duplicator nodes in Laffon's interaction combinators. Aux domain wires are implicit through the tree-like structure of the syntax, while aux wires are explicit through variable nodes, which are always paired. Additionally, main ports being implicit is critical to storing nodes efficiently in memory. Nodes can be represented as just 2 ports rather than 3. In HVM, since every port is 32 bits, this allows us to store a single node in a 64-bit word. This compact representation lets us use built-in atomic operations in various parts of the code, which was key to making parallel C and Q versions efficient. For details on the precise memory representation, see Section 7, 3.2. Interpretation of the syntax. Semantically, con, dup, and the array nodes correspond accordingly to Laffon's constructor, duplicator, and eraser symbols, and behave like mass as symmetric interaction combinators. The VAR node represents a wiring in the graph, connecting 2 ports of a net. They are linear and paired in the sense that every port is connected to exactly one other port, and therefore each variable occurs exactly twice. REF nodes are an extension to Laffon's ICs, and they represent an immutable net that is expanded in a single interaction. While not essential for the expressivity of the system, REF nodes are essential for performance, as they enable fast global functions, a degree of laziness in a strict setup, and allow us to represent tail recursion in constant space. Num, OP, and SWI nodes are also not essential expressivity-wise, but are too important for performance reasons. Modern processors are equipped with native machine integer operations. Emulating these operations with IC constructs analogous to Church or Scott numerals would be very inefficient. Thus, these numeric nodes are necessary for HVM to be efficient in practice. 4. Interactions. The ASD above specifies HVM's data format as a virtual machine that also provides a mechanism to compute with that data. In traditional VMs, these are called instructions. In term rewriting systems, there are usually reductions. In HVM, the mechanism for computation is called interactions. There are 10 of them. All interactions are listed below using Jensen-style rules. Note that these rules are symmetric. If a rule applies to a regex of tilde-b, then it also applies to b tilde a. Explanations and implementation details of each of the rules follow. 4.1. Link. Links 2 ports where at least one is a VAR node. A global substitution is performed replacing the single other occurrence of X with A. Recall that there is exactly one other occurrence of X in the net. In the graph writing system of interaction nets, linking 2 ports isn't technically an interaction, as wires are not named. However, for the term writing calculus, wires are named and must be substituted for. This is the only rule where nodes far apart can affect each other. See for details on the link function. 4.2. Call expands REF, replacing it with its definition. The definition is essentially copied from the static book to the global memory, allocating its nodes and creating fresh variables. This operation is key to enable fast function application, since, without it, one would need to use duplicator nodes for the same purpose, which brings considerable overhead. It also introduces some laziness in a strict evaluator, allowing for global recursive functions and constant space tail calls. 4.3. Void. Erases 2 nullary nodes connected to each other. The result is nothing. Both nodes are consumed, fully cleared from memory. The void rule completes the garbage collection process. 4.4. Erase. Erase is a binary node connected to a nullary node, propagating the nullary node towards both nodes and B. The rule performs a granular, parallel garbage collection of nests that go out of scope when the nullary node is an NUM or REF. The erase rule actually behaves as a copy operation, cloning the NUM or REF and connecting to both ports. However, when a copy operation is applied to a REF which contains DUP nodes, it instead is computed as a normal call operation. This allows us to perform fast copy of function pointers while still preserving interaction combinator semantics. 4.5. Commute. Commutes two binary nodes of different types, essentially cloning them. The commute rule can be used to clone data and to perform loops and recursion, although these are preferably done via calls. 4.6. Annihilate. Annihilates two binary nodes of the same type connected to each other, replacing them with two redexes. The annihilate rule is the most essential computation rule and is used to implement beta reduction and pattern matching. 4.7. Operate. Performs a numeric operation between two NUM nodes #n and #m connected by an OP node. If it is not an NUM, it is partially applied instead. There is only one binary operation interaction. Dispatching the different native numeric operations depends on the numbers themselves. See section 6 for details. Note that when counting the number interactions, operate 2 is not counted, as this would cause the number of interactions to be non-deterministic. 4.8. Switch performs a switch on the NUM node #n connected to a SWI node, treating it like a net equals 0. Here, it is expected to be a tuple with both cases, 0 and suck, and B is the return port. If n is 0, we return the 0 case and erase the suck case. Otherwise, we return the suck case applied to n1 and erase the 0 case. 4.9. Interaction table. Since there are 8 node types, there is a total of 64 possible pairwise node interactions. The interaction rule for an active pair is uniquely determined by the types of the two nodes in the pair. The table below shows which interaction rule is triggered for each possible pair of nodes that form a redex. Since the interaction rules are symmetric, this table is symmetric across the diagonal. SWI being common is problematic, should be removed, or the reduction for switch should change. Because for each active pair exactly one rule applies, HVM retains the same strong confluence that Laffon's interaction combinators do. This implies that not only can HVM programs be reduced completely in parallel, but also that the number of reductions is invariant to the order in which interaction rules are applied. This ensures that HVM can reduce redexes in any order without any risk of complexity blowups. 5. Substitution map and atomic linker. While HVM retains the strong confluence property of Laffon's ICs, locality is more difficult to obtain. This is due to HVM's variables. Variables link two different parts of the program and thus can cause interference when two threads attempt to reduce two redexes in parallel. For example, consider a subset of a net. Two threads attempting to reduce this net can be represented as follows. Thread 0, thread 1 of //c //eb//d/f. Notice that in the reduction of these two redexes, both thread 0 and thread 1 will need to access variables C and D. This requires synchronization. In HVM, there is a global collection of redexes that is mutated in parallel by a variety of threads. See architecture for details. Since every variable occurs exactly twice, the link interaction with the variable X will also occur twice, but possibly at very different times. The first time is when this variable is first encountered, and somehow a substitution must be deferred until the link interaction rule is applied to the second occurrence of X. This is accomplished by a global atomic substitution map. The substitution map keeps track of these deferred substitutions. That is, when a variable is linked to a node or to another variable, it is inserted into the substitution map. When that same variable is linked again, then the connection is made. It will already have an entry in the substitution map, and then the proper redex will be constructed. The substitution map can be represented efficiently with a flat buffer, where the index is the variable name and the value is the node that has been substituted. This can be done atomically via a simple lock-free linker. In pseudocode, this roughly looks like. To see how this algorithm works, let's consider, again, the scenario above. Assume we start with a substitution in number 42 and let both threads reduce a redex in parallel. Since both redexes are on any rule, their effect is to link both ports. Thus, the resulting net should be That is, E must be directly linked to number 42. Let's now evaluate the algorithm in an arbitrary order, step by step. Recall that the initial net is, and we're observing ports A, D, and E. Two links therefore must be performed. Link and link. There are many possible orders of execution. HVM a parallel evaluator for interaction combinators 11, 5.1. Possible execution order 1. 8. Number 42 equals thread 2. Link 8. Number 42D equals thread 1. Link 8. DD equals thread 1. Dot 8. Hash 42. Thus, deleted and link D. Number 42 equals thread 1. Dot D. E. Thus, delete D and link E. Number 42. The resulting substitution map is linking E to 42 as required. 5.2. Possible execution order 2. 8. Number 42 equals thread 1. Link 8. Number 42D equals thread 2. Link 8. Number 42D equals thread 2. Dot D. Thus, delete D and link 8 equals thread 2. Dot 8. Hash 42. Thus, deleted and link E. 42. The resulting substitution map is linking, again, E to 42, as required. 5.3. Possible execution order 3. 8. Number 42 equals thread 1. Link 8. Number 42D equals thread 2. Link 8. Number 42D E. D. In this case, the result isn't directly linking E to number 42, but it does link E to D, which links to A, which links to number 42. Thus, E is indirectly linked to number 42. While it does temporarily use more memory in this case, it is, semantically, the same result. Additionally, the indirect links will be cleared as soon as E is linked to something else. It is easy enough to see that this holds for all possible evaluation orders. 12. Victor Taelin. 6 numbers. HVM has a built-in support for 32-bit numerics represented by the annual node type. Numbers in HVM have a 5-bit tag and a 24-bit payload. Depending on the tag, numbers can represent unsigned integers, signed integers, i.e. 754 binary floats, or partially applied operators. These choices mean any number can be represented in 29 bits, which can be unboxed in a 32-bit pointer with a 3-bit tag for the node type. 6.1. Number tags. There are 3 number tags that represent types, and 15 that represent operations. Tag SYM syntax. UUIFF. Tag SYM syntax. As submod div rem eknek lieutenant GT and Azor flips of flip div flip ram. Finally, there is the SYM tag, which is treated specially and is used to cast between tags. 6.2. The SYM operation. The SYM operation is special. Its payload represents another numeric tag, and when it is applied to another number, it combines the stored numeric tag with the other payload, effectively casting the other number to a different numeric tag. For example, there's a SYM number with payload add, and when it operates on 1, it outputs. 6.3. You unsigned 24-bit integer. U numbers represent unsigned integers from 0 to 16,777,215. The 24-bit payload directly encodes the integer value. For example, 6.4. Assigned 24-bit integer. Our numbers represent signed integers from 8, 38, 8, 608 to 8,388,607. The 24-bit payload uses 2's complement encoding. For example, 6.5. F24-bit i.e. 754 binary float. F numbers represent a subset of i.e. 754 binary floating point numbers. The 24-bit payload is laid out as follows. CEMMMMMMMMM, where S is the signed bit, E is the 7-bit exponent, with a bias of 63, M is the 16-bit significant precision. The value is calculated as, if E equals 0 and M equals 0, the value is signed 0. If E equals 0 and M 0, the value is a subnormal number. 1s2, 620. M if 0 E 127, the value is a normal number. 1s2 E, 63 1. M if E equals 127 and M equals 0. The value is sign infinity if E equals 127 and M 0. The value is not int. F supports a range of about plus or minus 3. 4 times 1038. The smallest positive normal number is 2. 622.2 times 10. 19. Subnormal F numbers go down to about 1.4 times 10. 45. 6.6. Number operations. When two NUM nodes are connected by an OP node, the numeric operation is performed. The operation to be performed depends on the tags of each number. Some operations are invalid and simply return 0. If both number tags represent types, the result is 0. If both number tags represent operations, the result is 0. If both number tags are SYM, the result is 0. Otherwise, if one of the tags is SYM, the output has the tag represented by the SYM number and the payload of the other operand. For example, op equals 410 Victor Taelin. If one of the tags is an operation and the other is a type, a native operation is performed according to the following table. The result type is the same as the input type, except for comparison operators which always return U0 or 1. The number tag with the operation is the left operand of the native operation, and the number tag with the type is the right operand. Note that this means that the number type used in an operation is always determined by the right operand. If the left operand is of a different type, its bits will be reinterpreted. Finally, flipped operations interpret their operands in the opposite order. This allows representing, for example, both 1x and x1 with partially applied operations. OP equals plus 1, OP equals 1. Note that OP is a symmetric function. This makes the swap pseudo-interaction in opera valid. 7. The 32-bit architecture. The initial version of HVM as implemented in this paper is based on a 32-bit architecture. In this section, we'll use snippets of the Rust reference implementation of the interpreter available at the HVM repository to document this architecture. 7.1 Memory layout. Ports are 32-bit values that represent a wire connected to a main port. The low 3 bits are reserved to identify the type of the node whose main port the wire is connected to. This is called a tag. The upper 29 bits hold the value. The interpretation of this value is dependent on the tag. It is either an address, a virtual function address, an unboxed 29-bit number, or a variable name, or 0. Nodes are represented in memory as a pair of 2 ports. Notice that the type of a node is stored in the port. That is, ports store the kind of node they are connecting to. The global net structure includes 3 shared memory buffers. Node, a node buffer where nodes are allocated, vars, a buffer representing the substitution map, and RBAC, a collection of active redexes. A pair and a port are atomic variants of pair and port. Since this 32-bit architecture has 29-bit values, that means we can address a total of 229 nodes and variables, making the node buffer at most 4 GB long and the vars buffer at most 2 GB long. A 64-bit architecture would increase this limit to match the overwhelming majority of use cases and would be incorporated in a future revision of the HVM runtime. Since top-level definitions are just static nets, they are stored in a similar structure, with the key difference that they include an explicit root port, which is used to connect the expanded definition as target port in the graph. We also include a safe flag, which indicates whether this definition has duplicate or nodes or not. This affects the DUP-REF interaction, which will just copy the REF port, rather than expanding the definition when it is safe. Pubstruct def. Finally, the global book is just a map of names to defs. Pubstruct book. This concludes HVM's memory layout. For more details, check the reference Rust implementation in the HVM repository. 7.2 Example net. Consider, again, the following net, until at full. In HVM's memory, it would be represented as. Note that the vars buffers has only one entry because there are no substitutions, but we always use the last variable to represent the root port, serving as an entry point to the graph. 7.3 Example interaction. Interactions can be implemented in 5 steps. 1. Allocate the needed resources. 2. Load nodes from global memory to registers. 3. Initialize fresh variables on the substitution map. 4. stores fresh nodes on the node buffer. 5. Atomically links outgoing wires. For example, the commute interaction is implemented in Rust as. Note that, other than the linking, all operations here are local. Taking nodes from global memory is safe because the thread that holds a redex implicitly owns both trees it contains. And storing vars and nodes is safe because these spaces have been allocated by the thread. A fast concurrent allocator for small values is assumed. In HVM, we just use a simple linear bump allocator, which is fast and fragmentation-free in a context where all allocations are at most 64-bit values. 8. Massively parallel evaluation. Provided the architecture we just constructed, evaluating an HVM program in parallel is surprisingly easy. Just compute global redexes concurrently until there is no more work to do. HVM's local interactions exposes the original program's full degree of parallelism, ensuring that every work that can be done in parallel will be done in parallel. In other words, it maximizes the theoretical speed up for Amdahl's law. The atomic linking procedure ensures that points of synchronization that emerge from the original program are solved safely and efficiently, without no room for race conditions. Finally, the strong confluence property ensures that the total work done is independent of the order that redexes are computed, giving us freedom to evaluate in parallel without generating extra work. 8.1 Redex sharing. The last question, thus, is how do we actually distribute that workload through all cores of a modern processor? The act of sharing a redex is, itself, a point of synchronization. If this is done without enough caution, it can result in contention and slowing up execution. HVM solves this by two different approaches. On CPU, a simple task stealing queue is used, where each thread pushes and pops from its own local redex bag, while a starving neighbor thread actively attempts to steal a redex from it. Since a redex is just a 64-bit value, stealing can be done with a single atomic exchange operation, making it very lightweight. To reduce contention and to force threads to steal old redexes, which are more likely to produce long independent workloads, this stealing is done from the other end of the bag. In our experiences, this works extremely well in practice, achieving full CPU occupancy in all cases tested, with minimal overhead and low impact on non-parallelizable programs. On GPU, this matter is more complex in many ways. First, there are two scales on which we want sharing to occur. One within a running block, where stealing between local threads can be AC, accomplished by fast shared memory operations and warp sync primitives. 2. Across global blocks, where sharing requires either a global synchronization or direct communication via global memory. Unfortunately, the cost of global synchronization is very high. So, having a globally shared redex bag, as in the C version, and accessing it within the context of a kernel would greatly impact performance. To improve this, we, initially, attempted to implement a fast blockwise scheduler, which simply lets local threads pass redexes to starving ones with warp syncs. Such procedure is efficient enough to be called between every few interactions, allowing redexes to quickly fill the whole block. With that, all we had to do was let the kernel perform a constant number of local interactions. And once it completes, i.e., across kernel invocations, the global redex bag was transposed, letting the entire GPU to fill naturally by just the blockwise sharing function above, and nothing else. This approach worked very well in practice, and let us achieve a peak of 74,000 MIPS in a shader-like functional program. Unfortunately, it didn't work so well in cases where the implied communication was more involved. For example, consider the following implementation of a purely functional bitonic sort. Since this is an old algorithm, its recursive structure unfolds in such a manner that is much less regular than a tree map. As such, the naive task sharing approach had a consequence that greatly impacted performance on GPUs. Threads would give and receive misaligned redexes, causing warp local threads to compute different calls at any given point. For example, a given warp thread might be processing, while another might be processing instead. This divergence has the consequence of producing sequentialism in the GPU architecture, where warp local threads are in lockstep. To improve this, a different task sharing mechanism has been implemented, which requires a minimal annotation Redexes corresponding to branching recursive calls are flagged with A on the global book. With this annotation, the GPU evaluator will then only share redexes from functions that recurse in a parallelizable fashion. This is extremely effective, as it allows threads to always get equivalent redexes in a regular recursive algorithm. For example, if given thread is processing, it is very likely that another warp local thread is too. This minimizes warp divergence and has a profound impact in performance across many cases. On the bitonic sort example, this new policy alone resulted in a jump from 1300 MIPS to 12,000 MIPS. 8.2. Optimization. Shared memory interactions. GPUs also have another particularity that, if exploited properly, can result in significant speedups. Shared memory. The NVIDIA RTX 4090, for example, includes an L-cache memory space of about 128 KB. In GPU languages like CUDA usually allow a programmer to manually read and write from that cache and a shared memory buffer that is accessible by all threads of a block. Reading and writing from shared memory can be up to 2 orders of magnitude faster than doing so from global memory. So, using that space properly is essential to fully harness a GPU's computing power. On HVM, we use that space to store a local node buffer and a local subs map with 8,192 nodes and variables. This occupies exactly 96 KB, just enough to fit most modern processors. When a thread allocates a fresh node or variable, that 20 Victor Taelin allocation occurs in the shared memory rather than the global memory. With a configuration of 128 threads per block, each thread has a scratchpad of 64 nodes and vars to work locally, with no global memory access. This is often enough to compute long-running tail loops, which is what makes HVM so efficient on shader-like programs. There is one problem, though. What happens when an interaction links a locally allocated node to a global variable? This would cause a pointer to a local node to lead to another block, which would then be unable to retrieve its information, causing a runtime error. To handle this situation, we extend the link interaction with a leak subinteraction, which is specific to GPUs only. That interaction essentially allocates a global view of the local node, filled with 2 placeholder variables, such that one copy is local and the other copy is global. That way, we can continue the local reduction without interruptions. If another block does get this leaked node, it will be filled with 2 variables, which, in this case, act as future values which will be resolved when the local thread links it. The tilde leak x tilde by tilde b a tilde. The leak interaction allows us to safely work locally for as long as desired, which has great impact on performance. On the stress test benchmark, the throughput jumps from about 13,000 MIPS to 54,000 MIPS by this change alone. 9. Garbage collection. Since HVM is based on interaction combinators, which are fully linear, there is no global garbage collection pass required. By IC evaluation semantics alone, data is granularly allocated as needed and freed as soon as they become unreachable. This is specifically accomplished by the errors and void interactions, which consume subnets that go out of scope in parallel, clearing them from memory. When HVM completes evaluation, the memory should be left with just the final result of the program and no remaining garbage or byproduct. No further work is needed. 10. EO. To do. Explain how we do I/O. 11. Benchmarks. To do. Include some benchmarks. 12. Translations. To do. Include example translations from high-level languages to HVM. 13. Limitations. HVM a parallel evaluator for interaction combining. Towards 21. The HVM architecture, as currently presented, is capable of evaluating modern, high-level programs in massively parallel hardware with near-ideal speedup, which is a remarkable feat. That said, it has severe empathy for limitations that must be understood. Below is a list of many of these limitations and how they can be addressed in the future. 13.1. Only one duplicator node. Since HVM is affine, duplicator nodes are often used to copy nonlinear variables. For example, when translating the lambda term lambix, x plus x, which is not linear, one might use a DUP node to clone x due to interaction net semantics. Though, DUP nodes don't always match the behavior of cloning a variable on traditional languages. This if not handled properly, can lead to unsound reductions. For example, the lambda term, C equals lambith, lambix, which computes the church-encoded exponentiation 2-2, cannot be soundly reduced by HVM. To handle this, a source language must use either a type system or similar mechanism to verify that the following invariant holds. A higher order lambda that clones its variable cannot be cloned. While restrictive, it is important to stress that this limitation only applies to cloning higher order functions. A language that targets the HVM can still clone data types with no restrictions, and it is still able to perform loops, recursion, and pattern matches with no limitations. In other words, HVM is Turing complete and can evaluate procedural languages with no restrictions and functional languages with some restrictions. That said, this can be amended by 1. Adding more duplicator nodes. This would allow nested copies of higher order functions. With a proper type system, this can greatly reduce the set of practical programs that are affected by this restriction. 2. Adding bookkeeping nodes. These nodes, originally proposed by Lamping, allow interaction systems to evaluate the full lambda calculus with no restrictions. Adding bookkeeping to HVM should be easy. Sadly, this has the consequence of bringing a constant time overhead, decreasing performance by about 10x. Because of that, it wasn't included in this model. Ideally, a combination of both approaches should be used. A type checker that flags safe programs, which can be evaluated safely on HVM, and a fallback bookkeeper, which ensures sound reductions of programs that do not. Implementing such system is outside the scope of this work and should be done as a future extension. 13.2. Ultra-eager evaluation only. In our first implementation, HVM, we used a lazy evaluation model. This not only ensured that no unnecessary work was done, but also allowed one to compute with infinite structures, like lists. Since the implementation presented here reduces all available redexes eagerly, that means neither of these hold. For example, if you allocate a big structure, but only read one branch, HVM will allocate the entire structure, while HVM wouldn't. And if you do have an infinite structure, HVM will never halt. This applies even to code that doesn't look like it is an infinite structure. For example, consider the JavaScript function below. For equals x equals 0, 0, 1 plus foo. In JavaScript, this is a perfectly valid function. In HVM, if called as is, this would hang, because foo would unroll infinitely, as we do not detect that it is in a branch. To make recursive functions computable, the usual approach is to split it into multiple definitions, as in, foo equals x equals 0, foo z, foo s, foo z equals 0, foo s equals x equals 1 plus foo. Since REFs unfold lazily, the program above will properly erase the foo-s branch when it reaches the base case, avoiding the infinite recursion. Extending HVM with a full lazy mode would requires us to store uplinks, allowing threads to navigate through the graph and only reduce redexes that are reachable from the root port. While not technically hard to do, doing so would make the task scheduler way more complex to implement efficiently, especially in the GPU version. We reserve this for a future extension. 13.3. Single core inefficiency. While HVM achieves near linear speedup, allowing it to make programs run arbitrarily faster by just using more cores, its compiler is still extremely immature and not nearly as fast as state-of-the-art alternatives like GCC or GHC. In single-thread CPU evaluation, HVM is, baseline, still about 5x slower than GHC, and this number can grow to 100x on programs that involve loops and mutable arrays, since HVM doesn't feature these yet. For example, a single-core C program that adds numbers from 0 to a few billions will easily outperform an HVM1 that uses thousands of threads, given the C version is doing no allocation, while C is allocating a tree-like recursive stack. That said, not every program can be implemented as an allocation-free, register-mutating loop. For real programs that allocate tons of short memory objects, HVM is expected to perform extremely well. Moreover, and unlike some might think, HVM is not incompatible with loops or mutable types because it isn't a functional runtime, but one based on interaction combinators, which are fully linear. Extending HVM with arrays is as easy as creating nodes for it and implementing the interactions, and can be done in a timely fashion as a fork of this repository. Similarly, loops can be implemented by optimizing tail calls. We plan to add such optimization soon. Finally, there are many other low-hanging fruits that could improve HVM's performance considerably. For example, currently, we do not have native constructors, which means that algebraic data types have to be lambda encoded, which brings a twice 5x memory overhead. Adding proper constructors and eliminating this overhead. HVM, a parallel evaluator for interaction Combinators 23, would likely bring a proportional speed up. Similarly, adding more numeric types like vectors would allow using more of the available GPU instructions, and adding read-only types like immutable strings and textures with one interaction reads would allow one to implement many algorithms that, currently, wouldn't be practical, especially for graphics rendering. 13.4 32-bit architecture limitations. Since this architecture is 32-bit, and since 3 bits are reserved for a tag, that leaves us with a 29-bit addressable space. That amounts for a total of about 500 million nodes, or about 4 GB. Modern GPUs come with as much as 256 GB integrated memory. So, HVM isn't able to fully use the available space due to addressing constraints. Moreover, its 29-bit inbox numbers only allow for 24-bit machine instant flows, which may not be enough for many applications. All these problems should be solved by extending ports to 64-bit and nodes to 128 bits. But this requires some additional considerations, since modern GPUs don't come with 128-bit atomic operations. We'll do this in a future extension. 13.5 More work in progress. 14 Conclusion. By starting from a solid, inherently concurrent model of computation, interaction combinators, carefully designing an efficient memory format, implementing lock-free concurrent interactions via lightweight atomic primitives, and granularly distributing workload across all cores, we were able to design a parallel compiler and evaluator for high-level programming languages that achieves near-linear speedup as a function of core count. While the resulting system still has many limitations, we propose sensible plans to address them in the future. This work creates a solid foundation for parallel programming languages that are able to harness the massively parallel capabilities of modern hardware, without demanding explicit low-level management of threads, locks, mutexes, and other complex synchronization primitives by the programmer. References: 1. Lapham Y. 1997. Interaction Combinators. Information and Computation. 137, 69, 101. 2. Fernandez R. Marable and Mackey. 1999. Principles and Practice of Declarative Programming. Springer, Berlin, Heidelberg. 3. Salikmetov A. 2016. Token Passing Optimal Reduction with Embedded Readback. Electronic Proceedings in Theoretical Computer Science. 225, 45, 54. 4. Mass D. 2007. A Denotational Semantics for the Symmetric Interaction Combinators. Mathematical Structures in Computer Science. 17. 527. 62. Email address: Taelin@higherorderco.com.